Hello my dear PUC students, welcome to Deeksha Karnataka YouTube channel, and today is the first lecture of KCET Masterstroke, and we are going to discuss electric charges and fields. Now in Masterstroke basically we are going to give you one shot lecture of the entire chapter with some example problems as well, and this year I have also added the formula sheet at the end of the lecture, and if you want to download the PDF of today's lecture as well as if you want to get all the notifications that is happening in our channel, then definitely you have to join the WhatsApp channel. The link of the WhatsApp channel is given in the description section of this video. Click on the description section, read more and join the WhatsApp channel. Don't forget to join the WhatsApp channel. Everything will be supplied over there. Also, if you are watching our channel for the first time, then don't forget to subscribe and like this video. Now so we are basically discussing electric charges and field in one shot. So all the concepts along with some example problems will be discussed in this particular lecture. So let's see what are the concepts that we are going to discuss. That is the index of today's lecture: electric charge and properties of electric charge. Next, we will also discuss Coulomb's law. We will discuss electric fields and field lines. We will discuss electric dipole and dipole moment again, and lastly we will discuss electric flux, Gauss's law, its application, etc. Right? Now let's start. So first we will start with electric charge. The basics of the electric charge I hope you have studied in your lower classes, and many of you have already forgotten that. So let's refresh that memory. So there are two types of charges. You already know, positive and negative, right? What about these two charges? Like charges repel each other. What is the meaning of like charges? So like charges means if the charges are same, right? So if both the charges, say positive positive, are called like charges, and negative negative are also called like charges. What about unlike charges? Unlike charges, they attract each other. Unlike charges means suppose positive charge, negative charge, negative charge, positive charge. They are called unlike or opposite charges, right? So unlike charges or opposite charges, they attract each other. Like charges, they repel each other. Only electrons can be added or removed to charge any object. So if you want to charge an object, suppose we have a glass rod and we want to charge it. So what we can do from the glass rod, suppose this is our glass rod and we want to charge it, we can either add some electron or we can remove some electron. So only electrons can be added or removed to charge an object. Naturally an object is neutral. Neutral means it has no excess charge. Excess charge means, is it free of charge? No, it does have charge, but normally any material has equal number of positive and negative charge. So that means a neutral object. So neutral object means total number of positive is equals to total number of negative charges. Now if you make some imbalance in that, so if you add some extra electron, the number of electrons will be more compared to number of protons. So that's how you can charge the object to be negative. Similarly, if you remove the electrons, then the number of protons will be more and it will become a positively charged object, right? So if electrons are added to a body, it gets negatively charged, and if electrons are removed from the body, it becomes negatively charged. Positively charged. Okay, so if you are removing the electron, the body becomes positively charged. If you are adding the electrons, the body becomes negatively charged, right? Now gold leaf electroscope is a device which can measure the presence of charge. Okay, so basically it says that if the object is charged or not, that can be determined by gold leaf electroscope. Also there are some methods using which you can even determine whether it's a positive charge or negative charge, right? Now gold leaf electroscope and its working is no longer part of the syllabus, so I am not going to discuss in detail about it. SI unit of charge is Coulomb and its dimension is A into T. A is the dimension of current, T is the dimension of time, right? Let's continue. Now based on whether an object can carry electric charge or it cannot carry electric charge, we can divide it into two types of materials. One material is called conductor, another type of material is called insulators, right? Now why I am saying this, because we will discuss about a third type of material called semiconductors, that we will discuss briefly in current electricity chapter, and there is a dedicated chapter semiconductors. There we will discuss about semiconductors in detail. Okay, there we will also discuss about conductors and insulators and how they differ from each other. That exact property we will discuss in semiconductors chapter. Now for now only conductors and insulators. Conductors, charges can freely move through them. Okay, if charges can freely move through them, they are called conductors. Okay, basically they have a lot of free electrons. Okay, a conductor has a lot of free electrons. So free electrons means if the electrons are free, then only it can carry electricity, right? So if they are not free, if they are bound to the nucleus, they are not allowed to leave the house, so they are actually cannot carry the electricity. Examples are all types of metals and graphite. There are many other non-metal examples, but I have chosen only one simple example of graphite. Copper, aluminium, silver, they are all considered good conductors. Now let's move on. Charges given to a conductor always lies on the surface of the conductor. Suppose we have a conductor, and if you give it some charge, maybe positive or negative, the charge will always stay on the surface of the conductor. Inside the conductor, charge is always 0. Outside, charges will be there. Inside, charge is always 0. Remember this simple point. Okay, inside the conductor, the charge will be 0. Outside, charge 0 means positive and negative are equal. Obviously, 0 charge does not necessarily mean it is void of charge. Void of charge means no charged particle, but we know all material have atoms in it, and atoms basically have electrons and protons, equal number of electrons and equal number of protons. So whenever you charge a conductor, that means if you give it some excess charge, how can you give excess charge? Either you can add electron or you can remove electron. So once it is done, the charge in a conductor, that extra charge will always stay on the surface, it will not go inside. So for example, if you take a ping pong ball and if you put it on the water, the ping pong ball will always float on the water, it will not sink. So basically that is the meaning. So the charges are like ping pong balls and the conductor is like the water. Clear? Next we are going to discuss insulators. Charges cannot flow through them. So if charges are not allowed to flow through an insulator, through a material, that material is called insulator. They have almost 0 free electrons. So normally they do not have any excess free electrons that can carry the electricity. Okay, examples are plastic, paper, non-metals. Most of the non-metals are insulators. Plastic, paper are common example of insulators. So here, as you can see, one example here is we are using specialized material which is an insulator, which basically insulates the pole from connecting wire. Okay, so this is a conducting wire. You might think that how if you touch the electric pole, we do not get electrocuted unless and until there is some defect in the electric pole. So basically what happens when the conducting wire is connected to the electric pole, they are connected via insulating wires, and then there is a hanging wire. This hanging wire actually connects from this end to other end. So basically the pole is insulated, but it is not safe to touch any electric pole. Even though they are grounded, they have a lot of safety precautions, but in some cases there are some incidents where mishap happened. So don't touch an electric pole, it is not very safe. But anyway, they have safety mechanism in place, but you should not touch it unless and until it is required, right? So you should remember that the insulators also have some very good applications. For example, all the wires, the devices that we use in our day-to-day life, for example, the mobile charger, the charger cable is covered with insulating plastic so that you don't get shock when you touch it, right? So this is how every insulating object works. Now next is basic properties of electric charge. So how many basic properties are there? There are basically 3 basic properties. These are the points that you also are important for your PUC exam. So charges are additive in nature. So you can add charges like scalar quantities. Okay, charges can be added algebraically, right? So for example, q minus 2q plus 3q is equals to 2q. So this is a example of addition, how you can add charges. Charge is a scalar quantity. This also implies that charge is a scalar quantity. So for example, charge does not require direction. It only requires to add them algebraically. Next point, charges are conserved. Now charges are conserved always. Is it always? The total charge of an isolated system, very important to remember, total charge of an isolated system is always conserved. Total charge of an isolated system is always constant. So there is a question came in KCET few years back that charges is always conserved, charges is conserved for open system, charges is conserved for isolated system, charge is conserved only for any system. Now remember, charge is not conserved for any system, it is conserved only for isolated system. Isolated means which has no contact with anything else. Okay, for example, if you take a ball and if you keep it somewhere, that total charge on that ball will be conserved because it is not in contact with anything else. Okay, it is not possible to create or destroy net charge. Net charge means total charge. So it is not possible to create or destroy the net charge carried by any isolated system, although the charge carrying particles may be created or destroyed. So you can create, suppose an object has total say 100 electrons and say 90 protons. Okay, so what is the total charge? Net charge. Net charge is 10 extra electrons. Okay, so I'm just giving one example. So suppose an isolated system has 100 electrons and 90 protons. Okay, 90 protons. Now the net charge is 10 electrons, right? Protons are positive, electrons are negative, so total net charge is 10 electrons. This net charge cannot be changed, but you can somehow, there are processes in which you can change these electrons and protons. Suppose you have increased the electron by 10, then the proton will also increase by 10, the net will remain unchanged. The net will remain unchanged. Here you can change, but this one will should remain constant. Okay, so the total charge carrying particles can be created or destroyed, but the net charge cannot be created or destroyed. Okay, now last point, which is very important and student often confused, is that charges are quantized. Quantized means it has a fixed quantity. It cannot be any arbitrary values. Okay, that is called quantized. Quantized means, quanta means a fixed quantity. All free charges are integral multiples of a basic unit of charge denoted by small e. Small e is the charge of an electron, right? It is integral multiple means integer multiple. Integral means integer value. So if you multiply e with 1, e with 2, e with 3, all those charges are possible. But if I say if you multiply e with 2.5 or 4.5, that is not possible. 4.5, the decimal value is not possible, only integer value is accepted. Okay, so electron cannot be broken into smaller parts. Electron can always have as a whole number, right? So that's why charge always exists in the integer multiple of e, and that is final. So, and we sometimes write any charge, any given charge q equals to n into e. N can be 0, n can be plus minus 1, n can be plus minus 2, n can be plus minus 1000. So any value is possible, but it has to be a whole number. It will not be a fractional number. Okay, E is the charge of an electron and is given by 1.6 into 10 to the power of minus 19 Coulomb. Clear? Now, I will like to give you one example of this quantization. Suppose you have visited a milk shop. Okay, the milk shop sells only say half liter milk packet, and you went there, but your mother says, I don't require half liter, I require only 450 ml of milk, but the milk shop sells only half liter packet, that is 500 ml. You went to the shopkeeper and asked, my mother told me to buy a 450 ml milk. The shopkeeper says, will say that either you buy a half liter packet or you buy nothing. That is the minimum quantity that I have. You have to buy milk, whatever is the given in the packet. So quantized means the amount of milk in this packet is fixed, right? It has to be either 500 milliliter or 0 milliliter. Okay, you will not able to buy exact quantity that you require, right? Similarly, suppose you require now say 800 milliliter and you went to the shop, I require 800 milliliter. Shopkeeper will say you need to buy 2 packet of milk or you buy 1 packet of milk, but you will not get exact 800 milliliter. You have to buy 2 packet of milk, right? Similarly, if you require more, you have to buy whatever is there, you have to buy in the multiple of this minimum quantity of packet. You can say that this milk packet, 1 milk packet represents 1 charge of an electron, okay? Or you can have, so charges, total charge of an object will always be the multiplier of this electron charges. It cannot be a decimal point. You cannot have half of this packet. That is not possible. If you cut the packet in half, first of all, the seller will not sell you. Secondly, if you cut the packet in half of the milk will be wasted. And even when you are carrying the milk from the shop to home, more milk will spill, right? So basically that is not recommended. So what you can say is basically the electron has a shop and it is selling electron. If you want charge, okay, if you want charge, you have to have in the multiple of E only. I am not selling anything in change. Okay, change is not allowed. Half packet or half electron is not allowed. Clear? Now, let's move on and see one problem. A body has a charge of -4 microcoulomb. The number of excess electron it has. Now, this can be solved in 2 ways. First of all, the old way is you use Q equals to NE and you can find N equals to Q upon E. That is the old method, that is the common method. And in many cases, this method actually works. If you see this number is multiplier of 1.6. For example, 1.6, 3.2, 4.8. Okay, so if those values are given, you should use this method. Otherwise, there is a common method and much simpler method. That method is that you have to remember that if 1 coulomb charge is there, the number of electrons you need, okay, number of electrons that you need to add or remove. If it is a positive charge, you have to remove. If it is a negative 1 coulomb, you have to add extra charge, extra electron. Okay, either add or remove. So for 1 coulomb charge, the value is 6.25 into 10 to the power of minus 18. Plus 18. Okay, this value you have to remember. If you remember this value, this kind of problems always becomes easy, and this kind of problem comes in KCET from time to time. This is not one off question. This kind of question is very common in KCET. So if it is 1 coulomb, 6.25 into 10 to the power of 18 number of electrons. Either add or remove. As I mentioned, if it is a positive, you have to remove. If it is negative, you have to add. Okay, so here as you can see -4 microcoulomb, that means you have to add this much of electron. So how much electron you have to add? For 1 coulomb, this much electrons you have to add. So -1 coulomb. Plus means same, you have to remove. So -1 coulomb, you have to add this many electrons. So for -4 microcoulomb, how many electrons you have to add, or how many electrons you have to add? So very simple, 6.25 into 10 to the power of 18 into 4 microcoulomb. Okay, so what is 4 microcoulomb? Obviously you don't have to use the unit. So micro means 10 to the power of -6. Micro means 10 to the power of -6. So that conversion you have to remember. Okay, if it is only coulomb, you don't need to add this -6. 6. So 4 into 6.25 will give you 25 into 10 to the power of 12. So how many electrons you need? You need 25 into 10 to the power of 12 number of electrons to be added extra. So correct answer is 25 into 10 to the power of 18. And if you make some mistake, you might get any other options over here. Okay, remember micro you have to consider, and this value 6.25 into 10 to the power of 8. This is the shortcut method, one-step method. If you remember all such questions, you can answer. And in some cases, if you get the multiplier of 1.6, then you can use this method as well. You can try here as well, but as I said, you have to be little careful. So 4 microcoulomb means 4 into 10 to the power of minus 6 divided by 1.6 into 10 to the power of minus 19. So this can be tricky. Solving this can be tricky unless and until it is a multiplier of 1.6. Okay, so if it is a multiplier of 1.6, for example 3.2, in that case you can easily simplify it. Otherwise here it is not very simple. As you can see, it is 4 and 1.6, not directly cancelable. You have to cancel it, then you have to use at least one more line to simplify. But here you can directly multiply and simplify. Okay, now if you want to practice more such KCET level questions, and if you want to practice the time management, which is very, very essential, so then you have to consider our ABHYAS KCET test series. The time management in KCET is #1 priority. Okay, questions, if you practice, if you watch our lectures, and if you study a little bit, you should be able to answer those questions, but you may not be able to answer them in time. So answering the questions in time is very, very, very essential. Okay, so that's why we recommend our ABHYAS KCET test series. It is recommended by all the toppers. Last year the many toppers actually had benefited from our ABHYAS KCET test series. You can see their names over here, and they highly praise of our time management system. And if you are answering them, you will get a timer, and you have to answer the question based on that timer, which is very, very, very important. Also, this year you are going to get free of cost chapter wise KCET PYQs. So all the KCET PYQs chapter wise you are going to get for absolutely free, and entire cost is 1499. Okay, 1499. And what else you will get? You will get real exam pattern and timing. You will get total 35 KCET tests. Okay, out of that 4 of them are free. If you are not willing to purchase it right now, you can sign up for the free papers and see whether you are getting them or not, you are able to answer them or not. And PCM and biology is also covered in this series. So if you are only PCM students, you can skip biology, but if you are someone who also willing to give biology for allied courses, biology is also available. Now let's continue with Coulomb's law, another very important theory of this chapter. So first, before I start Coulomb's law, I have to define something which is called point charge. So we always say point charge, point charge, point charge. Is it exactly a point? Because charge can be an extended object as well. Charges are not always a simple point. Okay, charge can be a object as well. Now when we say point charge, okay, it is very important to understand that point charge does not necessarily mean it's simply a point. Point charge means if the distances that we are measuring, if compared to that distance, the size of the charged object is smaller, then we can consider it to be a point charge. Okay, so if distance is bigger than the size of the object, okay, then we can say this is a point object. Okay, so the size of the charged object is smaller compared to the distance, then that object is called point charge, and everything is considered to be located at the center of this object. Okay, that's how we actually came to know about point charge. Okay, point charge is basically everything is considered as at the location of the center, and if the distance is bigger compared to the size of the object, we say this is a point charge. Okay, now statement: the force acting between 2 point charges is directly proportional to product of the magnitude of the charges, okay, inversely proportional to the square of the distance between the charges. The force acts along the line joining the two charges. So let's see in detail. Suppose we have two charges, Q1 and Q2. They are separated by a distance, say small r. So what is the force between them? Okay, the force between them is given by 1 by 4 pi epsilon naught Q1 Q2 by r square r cap. What is r cap? R cap can be this unit vector. Then this will be our force. If you consider this as r cap, in this case this will be minus r cap and this will be minus a. Okay, so remember this. So if you are writing, this is a vector form of Coulomb's law, generally can be asked in your PUC exam. Anyway, so force is basically 1 by 4 pi epsilon naught Q1 Q2 by r square, magnitude wise. Vector form is given for someone, those who want to use this form in the PUC exam as well. Now K equals to 1 by 4 pi epsilon naught is also called Coulomb's constant. Here sometimes instead of writing 1 by 4 pi epsilon naught, we will write F equals to K Q1 Q2 upon r square. Generally K is in small letter, and this K is called Coulomb's constant. This K is called Coulomb's constant, and exact value of this can be calculated as 9.9 into 10 to the power of 9 Newton meter square per Coulomb square. Sorry, this square shifted a little. I will try to fix that in the PDF. So Coulomb constant, and its value is 9 into 10 to the power of 9. Approximately this is the accepted value. So if you are solving some questions, remember this value. This is very, very important to remember. Next, epsilon naught over here is called permittivity of free space. So how much electric field can pass through a free space, that is what is called permittivity, and it is given by 8.854 into 10 to the power of minus 12. Now remember, generally if a problem comes where you have to use the value of epsilon naught, it will be given in the question. Can be approximated to be 9 into 10 to the power of minus 12, but I don't ask you to remember this value, because many cases students often confuse this value and that value. So you should not do that. So you have to remember K, that is 1 by 4 pi epsilon naught as a whole. That value is given by 9 into 10 to the power of 9. You should not confuse this value and this value. This is only epsilon naught. So only epsilon naught has 10 to the power of minus 12 as minus. Here it is 10 to the power of 9, but it is plus. Okay, so don't make mistake remembering these two values. Okay, I have seen students, those specifically those who are starting now, have a tendency of confusing these two values. That you should not do. For medium of dielectric constant capital K, the effective distance in vacuum will be r root K. Suppose you take this system and you put the entire thing inside a dielectric medium. Dielectric medium means it's no longer a vacuum. So Q1, Q2, and the entire system in a dielectric medium of capital K. So don't confuse with this as well. This is a small k. This is Coulomb constant is small k, dielectric constant is written in capital K. Suppose you take the entire thing and immerse it into water, or immerse it into say some resin, okay, epoxy resin. Okay, so that they are considered to be dielectric medium. So if you put the entire system into dielectric medium, then the force, this formula is this exact formula is not valid exactly. So in that case, what you have to do, the force, the new force will be K Q1 Q2, it is small k, divided by capital K into R whole square. Okay, remember this. So the effective distance becomes r root K. Okay, r root K. Sorry, just small mistake. It will be r root K whole square. Okay, r root K whole square. So basically the force reduces. The force reduces. If you put this system inside a dielectric medium, the force reduces. So based on this, you might get a simple KCET question. Okay, this is very common type of KCET question. Now let's move on to electric field. So what is electric field? So in the previous case, we have seen two charges. Two charges were there, Q1, Q2. Now we have two charges, now capital Q, small q. Now if you have removed the small q charge, will there be any effect of this capital Q charge left over here? We had two charges, say capital Q and small q. Distance was r. Now if you remove this, so there was a force, right? There is a force acting on this. If this force is positive, this force will be negative by third law of motion, Newton's third law. Okay, equal and opposite reaction. So this force plus means this will be minus, but if you remove this charge, will there any effect of this capital Q charge be left there? Yes, it will be there. Obviously force is no longer there, force is gone, but there is some effect, and that effect can be understood if you put back any other charge over there. So what we are trying to do, we are trying to make at least one of the charge free. Okay, so we can put any charge over here and we can still feel the force, and that force can be calculated. So that force can be calculated using this formula, which is called electric field. So electric field, the effect of this charge, whatever is there, that effect is called electric field. Okay, this effect of this original charge is called electric field. Okay, the electric field due to a charge capital Q at a point in space may be defined as the force that a unit positive charge experience if placed at that point. So if you place a unit positive charge at this point, then whatever force that charge will experience, that is called electric field. Okay, alternatively, if a charge small q is kept, okay, inside the electric field E, then the force experienced by it is given by F equals to Q into E. So basically what we have achieved, that we have freed this charge small q. It can be small q, it can be capital Q, it can be Q dash, any charge. So if we know the electric field, we can calculate force. Okay, so this is same as Coulomb's force obviously, but here we are calculating the force in terms of electric field, not in terms of another charge. Okay, so that is very, very important to understand. Okay, so basically initially we started with two charges, now we have left with one charge, and soon we will see, we will remove all the charges, we will only focus on electric field. Electric field is more important and fundamental than charges. Okay, electric field key points, very important points to understand. The electric field due to a system of charge exists at every point in three-dimensional space. Each and every point up to infinity, the electric field exists. For a positive charge, the electric field will be directed radially outward from the charge. So if there is a positive charge, the electric field will be radially outward. These are not the properties, by the way. Okay, these are just the points that you have to remember. Negative charge, the electric field vector at each point points radially inward. So if the charge is negative, electric field always point in the inward direction, that is towards the negative charge. Okay, so if the charge is positive, the electric field is outward. If the charge is negative, electric field is inward. Now this concept is very important to solve numericals, especially the PUC level numericals. Positive and negative, the electric field concept is very, very important. Okay, it also important in KCET level, but in PUC level application is more common. Electric field due to a point charge is spherically symmetric. Okay, if the charge is point, you can draw a sphere around the point charge. Okay, and each and every point the electric field will be constant. Each and every point electric field will be constant. That's why it is called spherically symmetric. Magnitude wise same, direction will be different, but magnitude wise it will be same. Now when a positive charge is kept inside an external electric field, it experiences a force in the direction of electric field. Suppose we have an electric field. If you keep a positive charge, it will experience as a force in the direction of electric field. If it is a negative charge, it will experience as a force in the opposite direction of electric field. Okay, so positive charges experience as a force in the direction of field. Negative charges, they experience as a force in the opposite direction of electric field. Okay, now we are discussing the properties of electric field lines. The properties are important as well in your PUC. Field lines start from positive charges and end at negative charges. If there is a single charge, they may start or end at infinity. So if it is a single charge, single positive charge, it will start from the positive charge and it will go till infinity. If it is a single negative charge, it will start at infinity and it will go to, it can come back to the negative charge. But if we have a say positive charge and a negative charge, okay, electric field lines will always start from positive and it will always end at negative. It will never come in the opposite direction. Electric field are only one directional. It is not bidirectional. In a charge-free region, electric field lines can be taken to be continuous curves without any breaks. So as you can see, between positive and negative, there are no other charges present. So electric field lines are like this, continuous curves. It's not like this. Okay, this is not the way to draw electric field lines. Electric field lines has to be continuous curves in the charge-free region. Now these properties are also important for KCET. They will give you one or two properties and they will say identify the wrong property, wrong statement, or identify the correct statement. So one of the properties will be given correct, other three will be given incorrect, or vice versa. Three of them will be correct, one will be wrong. You have to identify the wrong statement. That's why properties of electric field lines are also important for KCET. A tangent drawn at any point on the electric field line gives the direction of electric field at that point. Suppose we have a electric field curve, and if we draw a tangent at this point, then we get the direction of electric field at this particular point, because it is a curve, right? So for a curve, how to find the direction? To find the direction, we have to draw the tangent. Two field lines can never cross each other. If they did, the field at that point of intersection will not have the unique direction, which is absurd. So if two field lines, suppose there is a field line, there is another field line, they cannot cross. Okay, cross between two electric field lines is not possible, because if they had crossed, then at the point of intersection, this curve will say electric field is in this direction, this graph will say electric field is in this direction. But electric field cannot be in two separate directions. Electric field at a point has to have a unique direction. Okay, this is the property of a vector. Each vector quantity has a unique direction, not multiple direction. Okay, electrostatic field lines do not form any closed loop. As I mentioned, it starts from positive, goes to negative. It does not form any closed loop. Electric field in free space decreases as we move in the direction of the electric field lines, and vice versa. Suppose we have field lines. Okay, so electric field is less over here and electric field is more over here. Based on this, we have seen one or two questions where the diagram is given. Okay, remember that as we are moving in the direction of electric field, okay, the electric field is moving from higher value to lower value. Okay, electric field is moving from higher value to lower value. So this is more, this is less. Okay, and if you go in the opposite direction of electric field, obviously you are moving from less to more. Okay, and equal distance of electric field represents, okay, uniform electric field. So variation is constant. So if you move say 1 centimeter here, suppose the change is say 1 Newton per Coulomb, and if you move 1 centimeter over here, then also it will be 1 Newton per Coulomb. So if the uniform electric field means it decreases constantly. It is still decreases, but it is decreasing constantly. That is the meaning of uniform electric field. Electric field due to a system of charge. Suppose we have a charge say Q1, we have another charge say Q2, another charge say Q3, so far and so on. We have another charge at some point Qi, and we have many charges up to Qn. Qi is some intermediate charges. and you are trying to find electric field at some point, say P. Okay, some of them can be positive, some of them can be negative. So what is the net electric field at this point? So for that, you have to join each and every point and you have to add them vectorially. Okay, you have to add them vectorially. Okay, you have to add these vectors in vector addition to calculate the net electric field. Okay, this is very common method. Now I am purposefully using more than 2-3 charges. Generally problem, if you see a problem, it will be 2 to 3 charges. So this is our point P. Okay, not this one. Now if you want to calculate the electric field at this point, you have to take individual electric fields and add them up. Okay, and the formula for net electric field will be E equals to N equals to 1 to N vector of EI. EI is the electric field due to one single charge, that is KQ by R square. Okay, so as I mentioned, formula is 1 by 4 pi epsilon naught Q by R square, but normally we do not write 1 by 4 pi epsilon naught, we write Q by R square. Okay, so this is the electric field due to a point charge, electric field to the system of charge. So individually you take all the electric fields and add them vectorially. Very, very important. Vector addition is important. You cannot simply add electric field. I have seen students doing it. You can do this for electric potential, but not for electric field. Electric field is a vector quantity, so you have to add them in vector method. Let's see one question. 3 small spheres, each carrying a positive charge capital Q, are placed on the circumference of a circle of radius small r to form an equilateral triangle. The electric field intensity at the center of the circle will be. So we have a circle and we also have a triangle inside this circle. It is an equilateral triangle. Okay, equilateral triangle. So here we have Q, capital Q, here we have another capital Q, here also we have another capital Q. So what is the net electric field at the center? So net electric field at the center, you have to calculate the electric field over here. Center of the circle will be center of the equilateral triangle as well. Okay, now if you calculate the net electric field, suppose this one will have electric field in this direction, then we have another electric field in this direction, and another electric field in this direction. Now according to Lamy's theorem I might teach you later on in PU1 where it is there. Okay, so if you see that the angle between them is 120 degrees, all the angles will be 120 degrees. Okay, and they are equal in magnitude, so they will actually cancel each other. So net electric field at the center will be 0. Okay, there is one more way to do that. If you take these two vectors, okay, if you take these two vectors, electric fields, and add them, you will get the net electric field in this direction, and you will have also equal and opposite electric field due to this positive charge. So positive charges always give electric field away. Negative charge gives towards. All the charges are positive, so the net electric field at the center will be 0, because the net of this and this is equals to this, which will be equals and opposite to the other electric field, and they will cancel each other. These two electric field will cancel each other, so net electric field is 0. Net electric field will be 0. Now electric dipole. What is electric dipole? Let's see. Two equal and opposite charges separated by a small distance is known as electric dipole. So two equal and opposite charges very clear. What about small distance? Small distance means of the order of micrometer, nanometer. Okay, millimeter is not considered to be very small, but micrometer 10 to the power of minus 6, nanometer 10 to the power of minus 9 can be considered. So equal, suppose two electrons, one electron and one proton are separated by a very small distance, then that can be considered as electric dipole. For example, hydrogen chloride. Okay, hydrogen chloride is a molecule. So what happens is that because of the higher electron affinity of chlorine, the electron pair which is being shared, one by hydrogen, one by chlorine, shift towards the chlorine, right? So this electron pair, the bond electron pair actually shift towards the chlorine. Chlorine takes the electron closer to it, and because it is taking the electron closer to it, it basically gains a small negative charge and hydrogen becomes slightly positive. Okay, so this is an example of electric dipole, because the distance between them, the bond length is very small. Okay, bond length is very small, so hydrogen chloride gas can be considered to be a electric dipole. So generally they are represented by this symbol plus q, minus q, and the distance between them is represented by symbol 2a. Okay, why 2a? Because if we are using this formula 2a, it helps us to calculate some of the formulas. Okay, remember, distance between them itself is 2a. So the distance between the dipole itself is 2a. So if you see a question where distance is given, okay, then you have to use 2a, not a. Do not multiply with extra 2 unless and until it is mentioned in the question. If it is mentioned half distance, then you have to multiply 2a. If it is mentioned only distance, then the 2a itself that distance. Now why it is important? Because we are going to discuss about dipole moment. Dipole moment basically is a measure of how strong a dipole is. Electric dipole moment is the product of magnitude of one of the charges and the distance between them. It is a vector quantity. So basically electric dipole moment is q into 2a and with a unit vector. So when in some problems you are given a dipole and the, two charges basically and a distance between them, and if you are asked what is the dipole moment, you have to multiply this 2a. So that's why I am saying if the distance is given while calculating dipole moment, you have to use 2a as a whole. Do not multiply extra 2. Be very careful. Okay. Now what is this n cap vector? So n cap is the unit vector from negative of the charge to the positive of the charge. Okay. Represents the direction of the dipole. So dipole moment is always points from negative to positive. Dipole moment always points from negative to positive of the charge. The unit of the dipole moment is Coulomb meter, not cm. Okay, not centimeter, it's Coulomb meter, capital C. Cm is small c small m. Okay, small c small m is centimeter. Capital C small m means Coulomb meter. Okay, don't confuse. Okay, last year in the board exam there was one small typing error where instead of typing capital C they typed small c. That created a lot of panic among students. But you should remember that dipole moment is basically Coulomb meter and its dimension is lat. Okay, lat. So lat is the dimension of dipole moment. Let's see one more example question. 3-point charges plus 2q plus 2q and minus 4q are placed at the corners ABC of an equilateral triangle. ABC of side x, the magnitude of the electric dipole moment of this system. Very interesting question. So we have a equilateral triangle ABC. Okay, we have plus q, plus 2q, plus 2q and minus 4q. They asked you what is the net dipole moment or equivalent dipole moment of this system. Okay, the distance is x. Equilateral triangle, so all the distances will be same. Equilateral means all sides are same, that is called equilateral triangle. What else? Equilateral triangle have all the angles also same, and that angle is 60 degrees. Right? These are all properties we know. Now how to find this? How to solve this question? To solve this question, we have to use a small trick, that we have to divide this minus 4q charge into two parts, minus 2q and minus 2q. So now these two will give me a dipole and these two will also give me a dipole. two equal charges, okay, two equal and opposite charges separated by a distance. This is called a dipole. So what is the dipole moment of this dipole? Dipole moment of this dipole is 2q into x. As I mentioned, do not add any extra 2. The charge is 2q, the distance is x itself, so 2a itself is x, so 2q into x is the net dipole moment of 1. What about the other one? Other one also have 2q, and the distance is again x, so this one will also have 2q into x. So this is the dipole moment 1, p1, this is p2. Now you cannot simply add them because they are vector quantities, so you have to add them vectorially. So what is the dipole moment of AC? So it is from negative charge to positive charge. So the dipole moment is in this direction. What about CB? Dipole moment is again from negative to positive. This pair does not form a dipole. Both of them are positive, so they does not form a dipole. Now basically what we got one dipole in this direction, P1. We got another dipole in this direction, P2. Okay, both of them are magnitude wise same. The angle between them is 60 degrees. So basically we have to add these two dipole moments using vector addition method. So what is the net dipole moment? Net dipole moment is given by, say, PR is resultant, that's why PR. It is given by P1 square plus P2 square plus 2P1 P2 cos theta. Sometimes we forget the simple formula, which is vector addition formula, a square plus b square plus 2ab cos theta. Okay, so now we have to put these values. Now for simplification, what we will use, both of them are same, so let us denote both of them by a common term p. So we get p square plus p square, otherwise the calculation can be little lengthy. 2p square cos 60. What is cos 60? Cos 60 is cos 90 is 0, so cos 60 is half. Okay, so cos 60, theta equals to 60 degrees, so cos theta equals to half. Okay, cos 60 is half, not root 3 by 4. Some of you might be saying. So half cancels and everything is addition. So it will be 2 plus 1, 3p square. P square plus p square plus p square. Right? 3p square. So it will be p into root 3. Now what is p? P is 2qx into root 3. Okay, or 2 root 3 qx. Now this kind of calculation you have to do it little faster because I am explaining each and every step, so I took little bit longer. But if I am solving the question, I will directly take both of them p and directly use the formula and solve it. Okay, so it will be 2 root 3 q into x. That is option A is correct. Now let's move on. The electric field due to an electric dipole on the points on the axis. So here we have two dipoles, plus q minus q, and we are trying to find the electric field at a point on the axis. Axis means let's change it because direction is from negative to positive, so let us take in the direction, so minus plus. Okay, if you want to does not matter anyway, formula in case of when you are deriving the formula, it does not matter. So the electric field at a distance p from the dipole, which is actually located at a distance r from the middle of the dipole, the electric field formula is given by 1 by 4 pi epsilon naught 2p by r cube. 2p is the p is the dipole moment. P is dipole moment. P equals to 2a into q or 2qa. Okay. Now remember, normally electric field is proportional to 1 upon r square due to a point charge, but for a dipole it is proportional to 1 upon r cube. Now derivation is part of your PU board exam, so those who are going to appear for PUC board exam, this derivation is important. Okay, you should practice it. Obviously this is a KCET series, so I am not going to do the derivation. If you want to know the derivation, I have done it in multiple other videos. You can check my Brahmastra series video. There I have done this derivation, which is obviously for PUC board. Now let's move on. for points on the equatorial plane. Some students find this derivation slightly tricky, so for that you have to, so suppose this is say positive charge, this is say negative charge, so electric field due to positive charge will be away, electric field due to negative charge will be towards, and then you have to take the component and add them. Okay, and the expression for electric field will be minus 1 by 4 pi epsilon naught P by R cube. Why there is a minus sign? Because dipole moment is from negative to positive and the net electric field is in the opposite direction. So dipole moment and electric field, they are in the opposite direction, that's why there is a negative sign. While doing the derivation you may not get this negative sign, but the negative sign will appear if you put the vector form. Okay, electric field is in this direction and dipole moment is in this direction. Okay, and again if you want the derivation, check my Brahmastra video on electric charges and field. There I have done this derivation. Let's move on. And one more thing, if you see that by magnitude, electric field on the equatorial plane is actually half of magnitude wise, it is half of the magnitude of axial. Okay, so equatorial plane, the electric field is half of that on the axial plane. Okay, this is also very, very important point to remember. There was a 2 present over here. If you go back to the previous derivation, previous formula, it was 2p by r cube, but here if you see it is only p by r cube. So that means equatorial plane is half of that of the axial. Dipole in an uniform external field. Now when you keep a dipole itself has an electric field, right? But if you take the dipole and keep it inside an external electric field, if you keep the dipole in an external electric field, the dipole will experience a torque. Torque means it's something similar to that of force but in a rotational motion. So basically when you apply force, object moves in a straight line. If you apply a torque, it moves in a rotational motion. That is basic difference between force and a torque. Okay, so in rotational mechanics, torque is there. In linear mechanics, in linear motion, force is there. So basically it will try to rotate in that electric field. Okay, so when you keep a dipole in an external electric field, there will be a torque acting on this dipole and it will try to rotate in this electric field. Okay, and that torque can be calculated as Pe sin theta. In vector form, P cross E, mostly Pe sin theta is the formula that you need to remember. Okay, so torque acting on a dipole is given by Pe sin theta. Theta is the angle between the dipole moment, which is negative to positive, okay, and the electric field. So this angle is theta. Okay, this angle is theta, the direction of the dipole moment and the electric field. Okay, not any angle, exactly this angle, okay. In uniform electric field means electric field is constant. If electric field is constant, okay, net force is 0. So there will be a force acting on this in the direction of electric field. There will be a force on this in the opposite direction of electric field. Okay, even though forces do not have an effect directly per se, but if the field is uniform, these two forces will be exactly equal and opposite. They will cancel each other, but torque will not be 0. Torque will not be 0 because they are not acting on the same object. They are acting on two different objects. Okay, so torque will still be there, but force, net force will be 0. If the field is non-uniform, then both force and torque are non-zero. Okay, so basically if field is not constant, so one charge will experience more force compared to the other, so the combination will also move in that direction of force. Okay, so it will be something very unique motion. Both force and torque are not 0. So torque is 0 when theta is 0 or theta equals to 180 degrees. So if it is aligned in the direction of exactly in the direction of electric field or opposite direction of electric field, torque will be 0. So theta 0, theta 180 degree, torque will be 0. Now let us move on to the next concept, which is electric flux. Another interesting concept, electric flux. So a fluid or liquid flowing with a velocity v through a small flat surface ds in a direction normal to the surface, the rate of flow of liquid is given by the volume crossing the area per unit time, v into ds, and represents the flux of the liquid flowing across the plane. So for example, we have a pipe. Through the pipe some liquid water is flowing, okay, in some direction. So the area of this is ds or delta s, and velocity of the liquid is v. So what is the amount of liquid which is coming out? The amount of liquid coming out per second is basically delta s into v. Delta s into v is basically is the amount of liquid which is coming out, right? Now in some cases the surface is not very flat, it is a curved surface, okay, it is like a curved surface like this. If it is simple flat, you can take whatever surface area is there and multiply with v, okay. But if it is flat, then what is the effective area? The area, you cannot take the entire area, okay, because liquid, even though liquid is coming out, you have to take the effective area, which is basically this one. So in that case what happens is that you take the area vector, and the velocity, and you take the flux. In this case will be given by v delta s cos theta, okay, this angle is theta, okay. If the surface is not upright, okay, exactly perpendicular to the direction of flow, then you need to take this direction and this direction and take the cos product of this, dot product of this. Basically dot product means cos theta. This is how you calculate the flux in case of liquids. Now the same concept can be applied for so flux is volume of fluid coming out in 1 second, v into ds, okay, and in this particular case it is v delta s into cos theta. Now if you replace this v with electric field, you get electric flux, okay. For the case of electric field, we define an analogous quantity and call it electric flux, which, okay, liquid flux is real thing where you can measure the volume of liquid which is coming out, but for electric field is not a physical measurable quantity, right? You can measure it, but it is not something that which is flowing like water, okay. So you may not be able to collect the electric field which is coming out of a surface in a container, right? So you have to that's why it is called an analogous quantity. Even though electric field is not something which is flowing, but electric field, if you go in the direction, the electric field magnitude varies, and that's why we use the same concept. If the electric field and delta s are perpendicular, it is given by E into delta s, okay, and if it is not perpendicular, if it is there is an angle between them, then it is given by E delta s cos theta or E dot ds, okay, E dot ds, E dot delta s. The dot product between electric field and surface area is the electric flux. The concept of flux comes from the fact of flowing water, okay. Now before moving on, there are few quantities that you need to remember: line charge density, surface charge density, and volume charge density. Just hold on for a few more minutes, the chapter is almost over. So line charge density means when you have a straight line, uniformly charged line, and you want to take one unit length and you want to see how much charge is there. That is called line charge density, and the unit of each densities are very, very important. So unit of line charge density is Coulomb per meter, and its dimension is L to the power of -1 A into T. Surface charge density sigma is Coulomb per meter square, and its dimension is L to the power of -2 A into T. Volume charge density Coulomb per meter cube, L to the power of -3 A into T. Okay, L to the power of minus 3 A into T is the volume charge density. Now let us move on to Gauss law. Statement: electric flux through a closed surface capital S is given by phi equals to Q by epsilon naught, or we already know that phi equals to E dot delta S, but for a closed surface you have to use a closed integration. This is closed integration. Closed integration means what? So if you start your integration, suppose we have a closed surface. If you start at a point and if you, after doing all the integration, if you go back to the same point, then it is called a closed integration. Okay, closed integration means starting point and finishing point are same. So Q equals to total charge enclosed by capital S. Okay, Q is the total charge enclosed by capital S. Now few points you have to remember specifically for MCQ of KCET as well as PUC exam. Gauss's law is true for any closed surface no matter what its shape or size. Okay, Gauss's law is true, you can say almost for any closed surface. Surface has to be closed, by the way. Here Q includes the sum of all the charges enclosed by the surface. The charges may be located anywhere inside the surface. Suppose surface is given like this, so some plus Q1 is here, plus Q2 is over here, plus Q3 at the center. Okay, some charge is over here. So basically Gauss's law says that Q is equals to sum of all charges enclosed. Okay, all charges enclosed has to be considered. Any charge outside, so this is all charge enclosed. Any charge outside will not be considered. Any charge outside will not be considered. Electric field is due to all the charges inside or outside. So if you are considering flux, okay, electric field on this surface, electric field will basically be with the charges inside as well as outside. Electric field is basically for both inside charge as well as outside charge, but the formula, this Q is actually only the charge which is inside. The surface that we choose for application of Gauss's law is called the Gaussian surface. Gauss's law is often useful to calculate the electric field for symmetric surface. Okay, for symmetric surface means, so for example cylindrical surface, spherical surface, some case cubical surface, they are all considered symmetrical surface, and Gauss's law are very good in those cases. But Gauss's law is not limited to symmetrical surface only, it is applicable to all types of surface, but symmetrical surfaces are easy to use. Next, field due to an infinitely long straight uniformly charged wire is given by E equals to 1 by 4 pi epsilon naught 2 lambda by R. Now here remember that uniformly uniformly charged wire is this one, infinitely long charged wire. Now in this formula, if you see, I have used 2 lambda because I have also used 4 pi by epsilon naught. Okay, so remember this is an easier formula to remember, especially if you are solving some numerical question. Okay, 1 by 4 pi epsilon naught 2 lambda by R. Okay, field due to an uniformly charged infinite plane sheet. So if you consider infinitely plane charge sheet, okay, where the charges are located on both sides, then the electric field is constant and it is given by sigma by 2 epsilon naught. It's a infinite sheet, it is again extended in all sides, then again electric field is constant, it is given by sigma by 2 epsilon naught. For obviously for long straight wire, electric field is proportional to 1 upon R, and for this electric field is constant. For a charge sheet, electric field is constant. For straight wire, it is proportional to only 1 upon R. So remember, for electric field due to point charge 1 upon R square, for dipole 1 upon R cube, for a straight uniformly charged wire it is 1 by R. So all three different cases are there, right? And the last case but not the least is the field due to a uniformly charged thin spherical shell. So if you are considering a thin spherical shell, shell means very thin material present on the surface, inside is hollow, inside nothing is there. Okay, so you can consider this is a spherical shell like egg, but you have taken everything inside the egg. Okay, only the covering is there, that is called a shell. So if you charge this shell, obviously inside the shell electric field will be 0. Inside the shell electric field will be 0 because no charge present inside it. Okay, and this same concept is applicable to a conductor as well. Electric field due to a conducting sphere or a simple spherical shell, both cases electric field inside is 0, outside it is given by 1 by 4 pi epsilon naught capital Q by R square. Capital Q is the charge, total charge on the surface of the sphere. Okay, so if you can calculate the total charge, you can calculate the electric field, which is given by 1 by 4 pi epsilon naught Q by R square. And if you draw the plot of entire thing, okay, then electric field is 0 up to this point. Electric field is 0 up to this point. Okay, because this is the point where the sphere ends. Okay, so radius is equals to capital R. So electric field is 0 over here. So electric field 0 means basically this is a 0 line. Suddenly it increases on the surface and it goes to 0 with proportionality constant 1 upon R square. So it starts from 0, it goes to 0. At infinity it becomes 0, but this is how the graph nature. You should remember the graph nature for exam, because there might be some question where you will be given the graphs and they will ask you which one is correct. Some cases they will extend it till 0, but remember for electric field it is 0 at the beginning and then it is going to 0. Now let's see one question. Consider a thin spherical shell of radius capital R. Okay, here radius is obviously this one, capital R, and distance, any distance is small r, and small r has to be greater than capital R. For less than capital R, E equals to 0. Consider a thin spherical shell of radius capital R consisting of uniform surface charge density S. The electric field at a point of distance capital small x from the center and outside the shell. So here is the shell. Okay, the radius is given by capital R, the surface charge density is x, and electric field at a distance capital X. What is the electric field? Is it proportional to S, proportional to x square, directly proportional to R, inversely proportional to x square? Let's see. So a lot of things are there. So the surface charge density is given, R is given. So what is the total charge on this surface? Total charge on the surface is given by surface area, that is 4 pi capital R square into S. This is the surface area, right? This is the surface area times charge density. This is the total charge on the surface. Now what is the electric field? Electric field is given by 1 by 4 pi epsilon naught Q upon x square. Q upon x square. So let's see, put the values. 1 by 4 pi epsilon naught 4 pi R square S divided by x square. So 4 pi cancels and we get 1 by epsilon naught R square S by x square. Okay, you can consider this to be as formula as well. Okay, so here as you can see, electric field is directly proportional to inversely proportional to S is wrong. It is directly proportional. Directly proportional to x square is also wrong. Directly proportional to R is also wrong because it is directly proportional to R square. Inversely proportional to x square is correct. So correct answer is option D. Okay, now here is the formula sheet for the chapter. I request you to use it wisely, right? All the important formulas are given one by one and all are mentioned in this chart. You can memorize it, you can understand all the formulas, okay, and you can take a printout of this formulas, 3-page formula. This is a long chapter, obviously 3-page formula, and you can keep it on your table to memorize them. Okay, the formulas will be helpful in your KCET exam, right? and all the best for your KCET preparation. If you have any doubts, any comments, any suggestions, don't forget to mention that in the comment section below. I'll be back with a new chapter very soon. Till then, bye.